Welcome everybody to our second Morse lecture of this spring. So you know the speaker already because I'm assuming you were here also for the first one in which I introduced her. And without further ado, let me give her the floor. She's going to talk about probabilistic analysis of random CSPs. Please, Nike.
Okay, thanks very much for coming back for the second lecture. So this lecture will not be self-contained because I'm going to talk about the same problem as in the last lecture, but I will try to make the third lecture, it will be about a different topic and it will be mostly self-contained. But today we're going to discuss the same model as last time of random deregular K not all equal set. So just to quickly remind you, the model is that we have a random graph where one side are the constraints or the clauses, and on the other side are the plus minus variables, which we get to choose. There are n variables. Each of them has degree d, meaning that it participates in d constraints. There are m clauses. Each of them has degree k, meaning that it contains k variables. And the number of edges is n times d, or m equals m times k. And each edge is labeled either plus or minus. So this graph with the plus minus labels on the edges, it encodes the problem. And then the solution space of this instance is the set of assignments x, which satisfy that x, for each clause A, the assignment of the variables which are incident to A does not match the labelings on the corresponding edges. And this has to hold for every clause in the graph. And we'll be interested in understanding the number of solutions of this problem.
Could I just ask a question? In the picture you have, could you have all yellows or all blues coming out of the same vertex, or you have always one of a different color?
No, the labels are just chosen IAD independently.
Okay.
And
so there could have been three blues coming out of one of these top vertices, right?
Oh yeah, sure, absolutely, yes.
Yeah.
Everyone is chosen independently.
Okay. Yeah. Thanks. Just want to be sure.
Yeah, thanks. So please just interrupt me at any time. Last time we considered this cavity method, which is a way of calculating heuristically what is the number of solutions. And the idea was that you start with a graph Gn, which is here. You choose a random subset of the clauses and you delete those. So you produce a cavity graph here, which has some variables which have one less degree. So each of them has degree d minus 1. And then you add back a new variable and some new clauses. And here you re-randomize. So each of these edges will get a new independent sign. And you consider what happens to the number of solutions as you go from here to here to here. So last time we saw how to do this, and the way to do this is to consider the uniform measure on solutions of this cavity graph, and to make the replica symmetric assumption, which is that we're going to assume that the variables in the cavity graph behave approximately independently of one another. So you approximately have a product measure here. Because the model is symmetric between plus and minus, it would just be 1/2 to the number of variables in the number of cavity variables. And we saw that if you make this simple assumption, then this gives a way to calculate how much the number of solutions will change as you go from one graph to the next. And you get this simple expression, and this is the replica symmetric free energy. In fact, what is true is that the number of solutions is equal to a function psi star of alpha, where it's equal to the replica symmetric prediction for alpha up to a certain threshold, Alphacon for condensation. But this naive approximation, it's no longer correct once alpha is larger than Alphacon. And the fact that this is wrong indicates that this approximation has to be wrong as well, and meaning that it's no longer true that these variables behave approximately independently. So the goal for today's lecture is to understand the structure of this measure, which again is the uniform measure on solutions of this graph, to understand this measure when alpha is larger than Alphacon.
Do you know Alphacon explicitly?
This is known, yes, yeah.
Okay.
So the story goes as follows. Again, alpha is the ratio of clauses to variables, and it's also the ratio of d to k. So first of all, for alpha,
sorry, so you said that you know it explicitly, but in each of the different models, I'm going back to your universality, you know it explicitly and they're different.
Yes, so actually Alphacon has been calculated for quite a large class of models. This is not in our work, but in work of Amin Pojaglan and some co-authors. So they have a general method to calculate the Alphacon for a class of models. In our work, it also follows the value of Alphacon for this model. It's the value of Alphacon will depend on the specifics of the model.
Right, and the other thresholds?
So the other thresholds, the value of alphasat is also known for various models, and again it depends on the specific model.
Okay.
Yeah. So the story roughly is the following. I want to try to explain the reason that this has a different structure when alpha is larger. And the idea is that when alpha is small, so here I should have clarified this is alpha dynamical. It does not mean that alpha is it does depend on d, but or sorry, yeah, it does not depend on d. So this is a different threshold which has also been computed, but this is not so relevant to this talk, so I won't focus on it so much. But when alpha is very small, the point is that there are not so many constraints. So you should have a lot of solutions, and the idea is that they mostly lie in a single cluster or connected components. So I drew a similar picture last time. So this box is meant to represent the discrete cube, and then this is supposed to represent the solution space. So two assignments are neighbors in the cube if they differ in a single coordinate. And then this big blob is meant to say that most of the solutions are close to one another according to that metric. So you can get from one solution to another by flipping one bit at a time and without leaving the solution space. However, once alpha gets large enough, this is no longer the case, and the solution space will consist of many well-separated clusters. And this happens quite a bit below the Alphacon that I'm talking about. So at roughly, it's roughly Alphacon divided by k, roughly of that order. You will have many well-separated clusters, meaning that to get from one clump of solutions to a different clump of solutions, you have to flip order n coordinates. And you have many clusters of different sizes. So here you have some cluster gamma 1, and its size e to the n s1, and this is a different cluster gamma 2, which is of size e to the n s2, and you have many clusters of different sizes which are spread throughout the cube, and this will happen as long as alpha is not too small. So then. Suppose that you knew that for all values of s, the number of clusters of size e to the ns is given by by e to the n sigma of s. So suppose that you actually knew this function sigma, and this is usually called the cluster entropy function. And if you knew this, then this would tell you everything about the solution space. So for example, the total number of solutions, you would just sum over the values of S, the number of solutions which are contained in clusters of that particular size. And this would be given by sum over S. This is the number of clusters of that size, and then this is the size of each one of those clusters. And so S goes over this limited range of values, and then these are on the exponential scale. So up to some poly n factors, it will roughly be the maximum over S plus sigma of S. And I just put here to emphasize that one should restrict to sigma of S being non-negative, because sigma of S being negative means that there are no clusters of that size. So we restrict to this range, and this gives the number of solutions. So if you know sigma, then it will of course tell you everything that you want to know about the solution space. So I will call S star the optimal value here, so the optimizer of S plus sigma of S. And then it means that most of the solution space, it will consist of roughly this number of clusters, and each of them will be roughly of similar size. It will be e to the n S star, and again, with some smaller order corrections. So here I just repeated what I said above. So there are two pictures that can happen. So for alpha below Alphacon, what happens is that sigma of S star is strictly positive, and this corresponds to having a large number of clusters. So the picture of sigma of S, this is sort of a cartoon of what it would look like. So S star is again it's the maximizer of S plus sigma of S. So it's a point where sigma has slope -1. And here sigma of S is strictly positive. So you will have exponentially many clusters, and the value of sigma S here is the exponent. And each of them will be of exponential size. Each of them will be of size roughly e to the n S star. So the picture is that you can have bigger clusters and you can have smaller clusters, but the majority of the mass of the solution space is taken up by these clusters, which are all roughly the same size, e to the n S star, and there will be exponentially many of them. And in this regime, the idea is that because you have so many clusters and they are kind of spread around the cube in a sort of diffuse way, it's sort of reasonable to expect that your measure, if you take the uniform measure over the solution space, that you would still enjoy correlation decay, because if I reveal to you that this variable is plus, it doesn't tell you so much about what another variable might be if that other variable is far away. So I'll contrast this with what happens when you're above Alphacon. So this whole curve, it depends on alpha. And as you add more and more constraints to the system, the curve will move further and further down. So when alpha is sufficiently large, the curve will have moved from up here to down here. And then the picture will be more like this. So the point where the maximizer of S plus sigma of S, if you don't restrict to sigma being positive, it will correspond to a negative value of sigma. So actually clusters of that size don't occur in the random system. And the clusters that do occur, they correspond to this point here where it's the last point where the function is actually positive. So sigma of S star is equal to 0. And based on this, it was predicted that the solution space will be dominated not by exponentially many clusters, but by order 1 clusters. So again, the picture here is that you have a lot of clusters. The total number of clusters is exponentially many. But the vast majority of the solution space will be dominated by just a bounded number of clusters. So there will be like 100 clusters that take up most of the solution space, even though the total number of all of the clusters is still exponential in n. So that's the picture that's expected in this regime. In this case, it's no longer reasonable to expect that you would have correlation decay. And the reason is that you can think about the extreme case where you have, for example, if you just had 2 clusters in your measure and say that they were both very small clusters. So maybe in the extreme case, each cluster is just a single point. And maybe one of the clusters is centered at the all plus configuration, and the other cluster is centered at the all minus configuration. This is a very extreme case of what you might have. So in this case, certainly you don't have correlation decay, because if I tell you that one variable is equal to plus, then of course it tells you that every other variable in the graph will be equal to plus. So it tells you things about other variables that are arbitrarily far away. So this is the extreme case, but because you have a bounded number of clusters, some version of this will be happening once you're in this regime. So you will have long range correlations. More is predicted. So there's quite a precise picture, which is that it's believed that the largest cluster weights follow a Poisson-Dirichlet distribution, and even the distribution is specified. It has a parameter m star, which corresponds to the slope at this largest point. This is called the Parisi 1RSV parameter, and there are some results on this in a recent paper. So I'm going to focus on the number of solutions and on the satisfiability threshold. So what will be the number of solutions? The number of solutions will be given by S plus sigma of S for whatever is the optimal value of S. And this is what is called the 1RSV free energy. So in particular, above Alphacon, this value is just equal to 0. So you have a bounded number of clusters. So the total number of solutions is roughly equal to just the number of solutions within any one of these clusters. So it's given by S star. Okay, so then the question is how to compute this sigma of S, because as I said, once you know the sigma of S, it will tell you pretty much everything you want to know about this model. And one way to compute it is to build a more tractable model for what is a cluster. So again, a cluster is we're going to view it as just a connected component of the solution space where 2 things are connected if you can flip a bit to get from one to another. And then we should ask why do solutions actually tend to cluster in the first place? And the reason for this is quite simple. And it's just because in this model, every variable belongs in a bounded number of constraints. So every variable participates in D constraints. So it means that a typical solution, it's going to have some positive fraction of variables which are free, meaning that you can flip them without violating any of the constraints that they participate in. And the picture is like this. So this is the instance G, and zoom in around a variable and say that this is the configuration on it. So this is a variable, these are the clauses that are around it, and then these are the variables that are around those. So the way that I wrote things, each of these clauses, because of the settings here, so for example, this clause, it's plus on here and plus on this edge, and this variable is set to minus and this variable is set to plus. So that means that no matter what value this variable takes, this clause is already satisfied because of the values of these other 2 variables. So from the point of view of this clause, this variable could be either plus or minus, it doesn't care. And it's true of each of the clauses that surrounds the variable. So this is what we call a free variable. When k is large, and when the degree is large, so it will participate in many clauses, and there will be many variables here. So it's not extremely likely for this to happen, but v and k are constant. So there will be some positive epsilon fraction where this does happen. And it suggests that x would lie in a connected component of size roughly 2 to the n epsilon, because if you have n epsilon free variables and you can flip each of them plus minus, so that would suggest that you have a cluster of this size. So this is not quite correct because it's possible that you have two free variables next to each other and they interact in some slightly non-trivial way. So for example, here you have two free variables which are neighbors. So each of them you can flip by itself and not violate any clause that it participates in. But because they are joined by a clause where these two variables are both minus, you cannot flip them both simultaneously. And you can construct larger examples where you have three free variables that are connected and so on. But it turns out that the incidence of these interactions is relatively rare. So the cluster size, it's not exactly 2 to the n epsilon, but it should be essentially that with a correction which is quite small as k is large. So however, if we want to know the precise asymptotics of the model, we do still need to work out what is this little order one term. So for this, we have to understand a little bit more about the structure inside of a solution cluster. So again, this is just repeating what I said before, that because you have these neighboring frees, it's not the case that a cluster is just like a subcube of the discrete cube. But the point is that it turns out that in the regime that we are studying it, the structure is still relatively simple. So we have a cartoon of a solution cluster, which looks like the following. So here is a single solution cluster, and this is what it will typically look like. So this is on the graph, and you have some variables which are free, as I said above. And then sometimes you will have a pair of free variables which interact in some non-trivial way. And sometimes you might have, a more complicated, so this is a sort of tree of free variables which are all linked together by these, because they're in clauses together and you cannot arbitrarily set them all independently of one another. However, most of the variables are actually frozen to some fixed value. So for most variables v in the graph, there's some fixed y sub v, which is either plus or minus, such that for every element within the cluster, it will just be forced to that value. So this is just to say that the clusters are pretty small in the regime that we are considering. So the majority of the variables, so 1 minus little o of 1 as k goes to infinity. So 1 minus a small fraction of variables, they will be just fixed always to plus minus. And the total proportion of this green stuff, which indicates the frees, it's small. Okay, so I will call F this subgraph of free things. And again, it's mostly just isolated free variables. So it's a single free variable. Everything around it is frozen to plus or minus. And then more rare are these sort of larger subgraphs where you have things that are linked. And to give a sense of the order of things, so the total number of free variables, so the total number of variables inside F, it will be order n divided by 2 to the k. But the number of free pairs will be something like n times k squared divided by 4 to the k. So it's much, much smaller. And the number of triples, it will be like divided by 6 to the k and so on. So because you have this type of decay, most of the components will be of bounded size. So it will not grow with n. And as a consequence, most of them have to be trees. So it's very, very rare that you will get a cycle of free variables. So this will happen with this will happen such that the total number of these within the graph will be order 1, whereas the number of these things within the graph is order n. So we're essentially going to neglect the effect of the free cycles. It's essentially all these trees. Okay, so again, why is this assignment outside of the free subgraph, which is frozen? So I'm just going to define eta to encode this. So I will call eta v to be yv, which when it's a frozen variable, and then when it's a not frozen variable, I will just set eta v to be f. So then, so what is gamma? Again, for most of the variables which are outside of f, the value is fixed. So it's eta v, which is equal to y sub v, which is either plus or minus. So this is just a fixed value. And then whenever you have a free tree, t, then you need to consider what are the solutions on this tree. And I denoted S of t to be the number of satisfying assignments on this tree, which are compatible with eta. So you have this, say that this is t. So if this is t, we're looking for assignments, for example, plus, 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 plus. Maybe this is a valid assignment. But in order to check if it's a valid assignment, it has to be compatible with the frozen boundary, which is around this tree. So this is what I mean by this S.
Excuse me for a minute.
Oh, sure, yeah.
Is it clear that once you start changing the tree, the frozen ones aren't going to be unfrozen? Like, isn't it possible that once you change the tree, some of the frozen boundary would now be like legitimate to change? Would be free?
So the way it's defined is that if it's frozen, it has to be frozen by something that's outside of the tree.
Okay.
So then it, yeah. So so if it's free, it means that that's right. Frozen means it has to be frozen by its neighbors.
Okay, thank you.
Okay, so then this means that gamma, it's not exactly a subcube, but it's not that much more complicated because it's a product of these singletons, and then these are kind of small sets that it's a product of. And then this also implies that the measure on gamma is not very complicated either. So if mu gamma is the uniform measure on gamma, then for the frozen variables, it's fixed, so that's very simple. And then for each of the trees, you choose a uniform assignment on the tree that's compatible with its frozen boundary, but you choose one independently for each of the trees. So this is the key point, that I choose a completion here, and I should choose a completion here, but there's no interaction between here and here. So they're independent of one another. So that is to say, two variables, they will be correlated only if they're inside the same free component T. And because we argued that most of these trees are bounded, this means that the measure has correlation decay. Because if you have one variable here and another variable here, and they're far apart, they should not belong in the same free component, so they will be independent under mu gamma. So that is to say that the measure mu gamma is replica symmetric. It has correlation decay. And this is sort of the one combinatorial kind of intuition for the 1RSB hypothesis, which is this hypothesis that I mentioned last time, that 1RSB says that you take the measure mu, it doesn't have correlation decay, but the claim was that you could decompose it into smaller components, but not too many of them, such that within each of those components, you do have correlation decay. And this is the argument for why you can do that, because each of these components, it's kind of this quite simple form that you have just the only correlation is caused by being in these kind of free subtrees, and there's not much more complicated than that. Okay, so let me try to describe the computation of the cluster entropy function. So this was this function sigma of S that I mentioned before. So this is here, I just repeated some of the things. So the only part we need to do is calculate what is the number of assignments of a tree, which is consistent with the frozen boundary. So this part I will not really discuss. It's just a computation of some, it's a sort of tree computation. So if you have an isolated free variable, then of course there are exactly 2 completions. And otherwise, you want to compute it in a way that you can read it off kind of nicely from the configuration eta. And this can be done by solving some sort of tree recursion. So this I won't go into, but the point is that if you want to know the cluster size, there's an easy way to read it off from this encoding eta. And it's just by solving some tree recursions. Okay, so then the cluster entropy function that we wanted to know, again, this was the number of encodings of a certain size in the exponent. So the physics approach for computing this thing is to consider this quantity. So you'll go over all of the encodings or all of the clusters, and you'll consider the cluster size, but raised to some power m. So if you know sigma, then this should correspond to summing over all of the cluster sizes, and then you have the number of clusters of that size, and then the cluster size, but raised to this power m. So we introduce this extra parameter m, and this will be optimized at the point s where sigma has derivative minus m rather than -1 as before. So the main thing that we gain from this is that actually this model, where you take the cluster and you weight it by its size to the power m, it should be replica symmetric, provided that you have many clusters of that size. And this should be true as long as you take m to be small enough. So m should be smaller than this m star, which corresponds to this slope here. So if you take m equals 1, then this is just the total number of solutions. And in that case, it does not work. So for m equals 1, it's not replica symmetric. But if you take m to be smaller, then you're somewhere here, for example. And here you do have a large number of clusters, which are of the correct size. And then it's reasonable to expect that the measure is replica symmetric. So as a result, for appropriate values of m, it's reasonable to apply the replica symmetric cavity method to calculate this Zm. So you couldn't do it when m equals 1 because you have long range correlations. But the idea was that if m is small enough, you should be able to do it. So you should be able to get some exact expression. And then once you know this, you can back out what is the corresponding sigma. So in a joint work with Alan Tsai and Yumeng Zhang, we used a similar idea to compute the free energy for the regular not all equal SAT model. However, for the rest of this lecture, I'm going to focus actually on the 1 RSV satisfiability threshold, which is a simpler problem. So if you don't want to know the number of solutions and you just want to know the satisfiability threshold, so you just want to know when do you have solutions and when do you not have solutions, then you don't really care about this entire curve, and you just want to know, I mean, the shape of the curve does not really matter so much. You just want to know when is the whole curve above 0 and when is the curve below 0. So if it's below 0, then it's not satisfiable. If it's above 0, then it is satisfiable, and that's all, right? So in that case, it's enough to evaluate just Z0, so corresponding to just the maximum point here, which is just the total number of clusters. So it corresponds to the maximum of this function sigma, and I'm going to call it phi star. So phi star is just the maximum of sigma. Okay, so going back to this encoding, so I argued earlier that if you have a cluster gamma, you can encode it by this plus minus free configuration, and it will satisfy the following rules. So if you have a plus minus value, that will be only if it's actually forced to that value by one of its neighboring clauses, and otherwise it will be free. So if you have a cluster gamma, you can map it to an eta, which satisfies these rules. But then you can also just say, forget about the clusters and let's just consider this is a well-defined model, right? So you can just ask, what are all of the etas which satisfy these combinatorial rules? Unfortunately, not every eta which just satisfies these rules corresponds to an actual cluster. So for example, the all free configuration, it does satisfy these rules. So no variable is forced to any value, and everything is free. So it satisfies these rules, but it doesn't correspond to any cluster. However, it turns out that there is roughly a bijection between actual clusters, which is what we're interested in, and these plus minus free configurations, which satisfy these rules, but also have the constraint that they don't have too many free variables. Because I argue that the fraction of free variables should be roughly 1/2 to the k. So if you have too many free variables, it's reasonable to expect that this is not a meaningful configuration. But it's possible to argue that if you don't have too many free variables, then this should correspond to an actual cluster. So I will call omega the set of configurations which satisfies these rules and have this fraction of free variables. And then if you take this omega, it's reasonable that it should be replica symmetric. So in the physics heuristic, you would just apply the cavity method to it. So you again take this GN, you go from GN to the cavity graph to GN plus 1, and you can calculate the change that you make at each of these steps, and it should give you some explicit function, and this should correspond to the thing that you want. And the satisfiability threshold, it should correspond to the point where this function will cross 0. So I'm going to talk briefly about this calculation. So when you do this calculation, the cavity measure, it's now the uniform measure on plus minus free encodings of the cavity graph, which have not too many free variables. And then the replica symmetric approximation, it says that you should approximate it by the product measure. So you have the cavity variables u, and it's approximately equal to the product of their marginal laws. So each of these is an element of plus, minus, or free. And again, we have some symmetry, so plus and minus are still symmetric with one another. So the chance to be plus and the chance to be minus, it should be some p, which is smaller than a half. But there's no symmetry with free, obviously, so we need to solve for this value. So once we have solved for this value, this will complete the heuristic derivation of this quantity, and it will give the satisfiability threshold. So I think that maybe in interest of time, I will skip the actual derivation of this quantity. So these are some references for this type of calculation. So let me just say very briefly how you derive the 1 RSV satisfiability threshold. So again, if you know this cavity measure, this will be enough to give the quantity that you want, because you can calculate from the cavity graph to Gn. It should be given by the chance that eta will be a valid configuration on the clauses that you add when you go from the cavity graph to Gn, and then the law of eta will be given by p, and likewise going from the cavity graph to Gn plus 1. And then you combine these two expressions to get the phi star. And then the only question that remains is to actually solve for the p. And this you can do by solving some tree recursions. So I'm going to skip this for now and go on to the proof approach. So the proof approach is by the moment method, and the idea of it is the following. So we want to know whether the model is satisfiable. So we would like to know that the chance that the number of solutions is positive. So this is the sum over all possible instances, the chance that you have that instance, and then the indicator that this instance is satisfiable. And the moment method is that you will calculate instead the expected number of solutions. So this is the average over instances, the number of solutions, and the expected squared number of solutions. So this is the second moment. So average over the graphs, the squared number of solutions. So this is what we want. And unfortunately, this is easier to calculate than what we actually want to know. But we have some inequalities that relate them. So first of all, the chance for z to be positive, it's upper bounded by the expected number of solutions. And then also the chance for z to be positive, it's lower bounded by the second moment divided by the first moment squared. So this is a consequence of the Cauchy-Schwarz inequality. So in the random not all equal SAT model, the expected number of solutions, it's very easy to calculate. So it's given actually exactly by the replica symmetric formula. And this is sort of a feature of this is partly due to the simplicity of the model. This is not the case for all models, but in this model, it is true that the expected number of solutions is exactly equal to the replica symmetric free energy. When alpha is not too large, it is possible to show that the second moment and the first moment squared are comparable to one another up to constants. And as a result, by the second moment inequality, the probability for the number of solutions to be positive is lower bounded by some constant. And this can be improved to with high probability by some Fourier analytic arguments. So the moment method, it was first applied in the context of random CSPs by Archioptis and Moore, and then there were many subsequent developments by these people. But as I already noted, for alpha larger than Alphacon, the correct number of solutions, it should be much smaller than the replica symmetric value. So it's much smaller than the expected number of solutions. And this indicates that the direct moment method is going to fail in this regime. And one way to see that is that for alpha larger than Alphacon, the expected number of solutions, it's dominated by this rare event where you have an atypically large cluster. One way to see that is to understand this curve as being related to the expected number of solutions. So then if you optimize over the entire curve, you end up somewhere here, but it corresponds to a cluster size which does not show up in the typical picture. So instead, the solution is to not apply the moment method to the number of solutions, but to apply it to the number of clusters, or rather by the number of clusters as encoded by these plus-minus free configurations. And a similar approach was already explored back in around 2001 by Kojaglan and Panajatu. And under the 1RSV heuristic, the moments should be equal to roughly the free energy of this problem. So what has been shown in some of the rigorous work, so for this particular model, we did compute the first and second moment, and we showed that it corresponds to this value 5 stars. So this gives the satisfiability threshold for this model. We also have an analogous result for maximum independent sets. I mentioned the free energy result for the same model. And then finally, we have a result for the satisfiability threshold in random KSAT. But this is a more complicated model. So the approach that I describe here of doing this, it will not work in this model, and this requires further work. But even for this work, we have the same starting point that we take this set to work with. So in the time remaining, I will talk about what goes into the proofs. So actually, in all of the mathematical results on this problem, most of the difficulty is in the actual moment computation. So in evaluating the expected number of clusters and the expected squared number of clusters, for example. And this is just because the constraints of the plus-minus free model, they're somewhat more complicated than those of the original model. And it's more difficult to deal with. So in order to compute this, one thing that's quite useful is there's a known bijection between these encodings, which are defined on the variables of the graph, with some other configurations, which are called colorings. And I described the bijection here, but actually I'm not going to use anything about this bijection. The only thing I want to emphasize is that the spins for this model live on the edges of the graph rather than the variables. So why is it important that the spins are on the edges of the graph? So given this configuration where the spins are on the edges of the graph, I'm going to define an empirical measure which is associated to it, which is I'm going to count what fraction of variables have incident colorings given by this, what fraction of clauses have these incident colorings, so this is a k-tuple, and what fraction of edges have this coloring. So for example, this new dot, it's a probability measure on these d-tuples. This is a collection of summary statistics about your configuration. And note that the number of configurations, it's exponentially large, but the number of the summary statistics is polynomially large. So the main point of moving from configurations that live on the variables to configurations that live on the edges is that it's easy to calculate the expected number of configurations that correspond to a given nu. And it's given by just a simple combinatorial calculation. So this is the number of ways to assign variables with empirical measure nu dot. This is a number of ways to assign the clauses such that it has empirical measure nu hat. And then this is the way that this is a number of ways to match up the edges such that it will be consistent. So once you do this and you apply the Stirling approximation, you have just an optimization problem. which is given in a quite explicit form. So it's the Shannon entropy of nu dot plus alpha times the Shannon entropy of nu hat minus d times the Shannon entropy of nu bar. So it's a very explicit expression. And the only complication is that these measures live on slightly complicated spaces. Unfortunately, it's not a convex function. So this part is convex and this part is convex. So it's a convex function minus another convex function. So that doesn't help us very much. So it is true that it's convex if you fix this term. So the main difficulty is to determine what is the best way to assign the edge marginal. So you want to determine what is the best empirical distribution on the edges, and you want to show that this will correspond to the replica symmetric value. Analogously, there's a similar expression in the second moment, except that now the spins live in this a squared rather than a. So for the second moment method to work, you need to show that the second moment is comparable to the first moment squared, which means that you need to optimize this function. And usually, in order for it to equal the first moment squared, it means that you need to show that the optimal empirical measure is a product measure, and the marginal should be given by whatever was the optimal measure in the first moment. So the point is that you can, when you do the moment method, it naturally leads to this optimization problem and this optimization problem. And they're explicit functions, but they're not very nice. So for example, in the second moment, you have an optimization over something like 24 dimensions. So it's not like a very high dimensional problem, but it's certainly enough high dimensions that it's not clear how to do it. And the strategy that we take to do it is roughly the following. So again, I want to optimize either this psi or this psi2. So I'm going to talk about how to optimize psi, but it's the same strategy for psi2. So just broadly, the strategy is that first, so it's not a convex function, but you have some combinatorial estimates that you can do. So you do as many of these sort of rough estimates that you can, and you try to show that the optimizer has to be reasonably close, so within some epsilon of the thing that you hope to be the maximizer. So you can figure out what you hope to be the maximizer by solving some tree recursions, and then you want to show that the maximizer must be pretty close to that. Then once you've localized it to this small region, then you have some hope to show that actually the function is convex when restricted to that region and has a unique maximizer, which is what you want. So I'm going to briefly discuss this second step, which we do by a sort of localized update procedure. And the idea is that because it's a convex function, you can hope to optimize it by kind of making some sort of gradient descent type of step, although it's you will see it's not exactly gradient descent, but it's a similar type of idea. So the approach is something like the following. So take your large graph Gn and consider choosing a subset of n variables from it. So these are the n variables, which are the roots at the top here, and take y to be their depth 1 neighborhood. So y are these trees, which are in purple. And then consider these edges, which are distance 1 away from the variables that you chose. And consider just cutting these edges. And so they separate from the rest of the graph, and call this G delta. So we can think about the expected number of configurations on the graph. One way that you can decompose it is fix the empirical measure on the cut edges. once you know the empirical measure here, you can randomize separately what is above and what is below. So below, I have some complicated random graph, which I don't understand. But the point is that above, it's something very simple. So here I have some fixed empirical measure of colors, and I re-randomize the structure which is above. So I'm going to re-randomize these edges. So I will cut these edges and, for example, rematch this edge to this clause. And I will also re-randomize the plus minus signs of the edges which are above. And I can do this separately from what is below the line. So now just fix the empirical measure on the boundary and consider what is happening only above the cut line. So what is the expected number of configurations above? This corresponds to the maximum entropy measure, such that the measure has marginals which are consistent with the empirical measure on the cut edges. So you have many of these trees, but each of them is a copy of the same tree here. And you just want to find the maximum entropy measure on this tree subject to a certain boundary marginal. And the point is that once you're on a tree, this is actually a convex problem. It has a unique solution which we can calculate. It depends on the boundary measure nu bar that we specified. So whatever is the measure nu bar here, you can just solve for what is the maximal entropy measure on the tree that corresponds to that. But on the other hand, because there was nothing special about the variables that we chose to be on top, because the graph is invariant to permuting the labels, then it means that whatever the measure P is, it should be symmetric. So the law here should be the same as the law here, because there's nothing special about the edge being above rather than below. And then the goal is to show that unless nu bar is equal to the thing that you want it to be, unless that happens, you can show that in fact this measure here and this measure here will not be equal to one another. And as a result, it implies that the optimum measure will be equal to the one that you want it to be. So these are a little bit more detail on the constrained maximization problem, but I think I'm running out of time. So I will just briefly summarize the steps, which is that we want to do moment method on clusters, and we reduced it to this optimization problem, which is difficult because it's not convex. But first of all, you make some combinatorial arguments to localize it to nu being within a small region or to mu being a small region. So you have a hope of it being convex. And in that region, you can reduce the problem to maximizing entropy on trees with some fixed measure on the boundary. And this is a convex problem. And it can be analyzed by considering tree recursions. So the idea is that you start with this kind of complicated problem that you don't know, and in the end, it reduces to analyzing tree recursions, which are easier to do. And most of the difficulty is to analyze the tree recursions that arise in the second moment calculation. And this is one of the reasons why the coloring model, I think, has not been solved yet, because it involves more complicated recursions. So next time at the start of the lecture, I will just say very briefly why random k-sat is more complicated than what I described today. But I won't talk about random k-sat too much. And most of the next lecture, I will talk about the perceptron model, and I'll say why it's analogous to random k-sat, but it's an easier model, and I will explain the solution for that model. Okay, and I'll finish here today. Thanks a lot.
Thank you. Questions?
When you do this optimization, eventually, is it on a computer or is it by hand?
It's not on a computer. It's by hand.
So when you localize and each piece is convex, you can do it. I mean, how many cases do you have to consider? How many regions?
It's more complicated for a random k-set, but for this model, it's not too bad. It's just the estimates are just of the type roughly that it's not much more complicated than estimates of the type the fraction of free variables should be of order 1/2 to the k. The fraction of plus minus, it should be roughly equal to one another. Maybe
so why were you talking about gradient methods and things? You never, so there's no computation.
No, I only mean it's somewhat analogous to a gradient method in the sense that this is like a local update procedure.
Yeah.
It's like a one-step update.
Mhm.
So only in a very loose analogy.
Okay.
Yeah.
Other questions?
I was going to ask you about something you mentioned in passing, which is this Poisson-Dirichlet statistics. Is this something that's, yeah, I mean, I guess this is not proved yet, or it's conjectured. Is that, what's the status?
Yeah, I guess Alan might be here, so maybe he can comment. I think
yeah,
it was
it's not proved. Yeah.
But it's
I think there's
expected. But so and the parameter of the Poisson-Dirichlet process is it's not a simple one. It's not your standard one. It's not your usual Poisson. You have a parameter. Is that right?
That's right. But
and is this going to be common for many of these mean field type models?
it should be, yes.
So it's not particular to this particular model. You'll have it in other cases.
No, I mean only the value of M is particular to this model,
of course.
but otherwise it's the same distribution.
No,
always.
by the way, it occurs in many non-mean field systems at low temperature, like quantum Heisenberg and so forth, and other models with different symmetries where you have symmetry breaking. You're expected to have Poisson-Dirichlet. Again, it's not proof, but yeah, it's interesting that it appears here too.
Yeah, I don't know if in some, I guess in the p-spin model it is proved in some regime.
I don't know. Does Alan, do you know?
I think so, but yeah. Yes.
I was under the impression for the p-spin model at low temperature it is known, but I'm not the right person to ask for that.
Because that's the kind of universality that you might think of being associated with these models, right? I mean, to have these kind of statistics.
Yeah, it's certainly expected to have this type of
analogous to what you have in random matrix theory, where you have this. Yeah, it's really quite similar.
Yeah.
For, if I may, for the p-spin, the hard p-spin at very low temperature, it won't be Poisson-Dirichlet because it's supposed to be full RSB. So, but it's but for the
that's
p-spin,
right. And is it
for the p-spin spherical, it is. I think it is proven by the Subag result at very low temperature.
I see.
But am I mistaken? Hi, am I mistaken? Poisson-Dirichlet is a stepping stone towards a richer class of universally relevant distributions, which have the structure of this generalized random energy model.
Yes, that's right. So, I mean, this is just a one level.
That's the universal, more universal feature common to these different problems, potentially.
Yeah, you have it, of course, for the random energy model. That's because it's the paradigm of 1 RSB.
Can I ask a naive question?
Yeah, sure.
So in the space where you're choosing a subset of n variables from Gn, is there anything that sort of what are the constraints on the choices of the n variables that then allow you to ensure that the sort of smaller object that you're working with is enough?
Yeah, that's right. This is sort of a cartoon of how the argument actually goes, because certainly it's possible that you choose n variables and by chance 2 of them are very close to one another, and that would be a problem certainly for the argument. So this is not should not be viewed as a literal thing. So, but the idea is that if you choose n variables and n is pretty large, so the little n should be large, but it should be much smaller than the total number of variables. So it should be the case typically that they're all kind of far apart from each other. So this bunch and this bunch will not interact with one another typically. And then the idea is that because little n is large, this empirical measure should be pretty close to the overall empirical measure of the entire graph. If you consider this re-randomization step, the idea is that what you started from and what you ended from, what you end up with, because you re-randomize within the model, it should look similar from start to finish. But it turns out that it will not be similar unless the measure here is the ideal one that you want it to be. That's roughly how the argument goes, but it is true that there are some restrictions on the Y.
Thank you.
Hi, Nike. I have a question. So the assumption that K is large, so you showed that in the beginning that you use it crucially to show that the structures of 3 variables is subcritical, the graph of 3, so it's mostly composed of trees, right?
Yeah, that's right.
And is that the only place, is that the most important part where this assumption is used, or are there other steps of the argument where the assumption of K large is used?
I believe this is the most important part.
Yeah,
I think it is essentially the only part where K large is used.
Got it. Yeah. Thanks.
Are there any other questions? Well, that does not seem to be the case. So thank you, Nike, again. And I will see everybody on Friday, I guess.